Permutations rule. When some items are identical to others. When n items are all selected without replacement, but some items are identical, the number of possible permutations where order matters is found by using the following rule. The number of different permutations where order counts when n items are available and all n of them are selected without replacement, but some of the items are identical to others is found as follows. We would have n factorial divided by n subscript 1 factorial times n subscript 2 factorial all the way to n subscript k factorial, where n subscript 1 are alike, n subscript 2 are alike, and n subscript k are alike. Now let's take a look at example 4, which is permutations rule with some identical items. Survey design. Now, when designing surveys, pollsters often repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one survey with 10 questions, 2 of the questions are identical to each other with superficial differences in wording, and 3 other questions are also identical to each other with superficial differences in wording. For this survey, how many different arrangements are possible? And is it practical to survey enough subjects so that every different possible arrangement is used? Now, we have a total of 10 questions with 2 that are identical to each other and 3 others that are also identical to each other. We want the number of permutations. So we know the value of n is going to equal 10. N subscript 1 is equal to 2 because there are 2 that are identical. N subscript 2 is going to equal 3 because there are 3 that are identical. So we're going to use the rule for permutations with some items identical to others. So we have a total of 10 questions with 2 that are identical to each other and 3 others that are also identical to each other. We want the number of permutations. Now we know that n is 10 questions. We know that n subscript 1 is 2, and we know n subscript 2 is 3. So we're going to use the rule for permutations with some identical items to others. And so we're going to get the following. Okay, first we know the following. We know that n is going to be 10, and then we have n1, which is going to be 2, and we know that n2, which is going to be 3. So let's go ahead and do that. So we're going to fill that in. So we know that this is going to be 10 factorial divided by 2 factorial times 3 factorial. Okay, now if we simplify the 2 factorial in the next step, we're just going to get the value of 2. Okay, now we're going to leave 3 factorial alone so that we can then expand 10 factorial. We're going to expand 10 factorial to be 10 times 9 times 8 times 7 times 6 times 5 times 4, and then times 3 factorial because we can simplify those two. So simplifying the 3 factorial, we have a 1 here and then a 1 here. And now simplifying the 2 into the 4, we have a 1 left over from the 2, and 2 goes into 4 2 times. So now we can write the following. We can then write in the numerator 10 times 9 times 8 times 7 times 6 times 5. That 4 now becomes a 2 and then times 1. In the denominator we have 1 times 1, which is 1. Now when we multiply all those numbers out, we end up getting 302,400. Now the interpretation is as follows. There are 302,400 different possible arrangements of the 10 questions. Now, it is not practical to accommodate every possible permutation, so for typical surveys, the number of respondents is somewhere around 1,000.